Today, we're going to tackle a classic physics problem that really stumps a lot of students. But I promise, by the end of this short explainer, you'll see it all just boils down to one key insight. Okay, let's dive in.
The challenge we're looking at today isn't just any old textbook question. It comes from a book that has been a rite of passage for physics students for decades. It's a real classic.
Yep, this is the book. If you've ever studied physics, you've probably heard the name Irodov. His collection is famous for being incredibly tough, but also for building a really solid understanding of the fundamentals.
And here's our challenge, problem 1.87. Now, on the surface, it sounds simple enough, right? A body slides off a sphere. What's so hard about that? Well, this is a classic gatekeeper problem. Solving it proves you really understand the concepts, not just how to plug numbers into formulas. So, how would you even begin to approach this? Well, the first step in pretty much any mechanics problem is always the same. You have to visualize the situation and then draw your forces. So let's get that set up right first. We have two main forces at play here. First, you've got gravity, mg, which is constant and always pulling straight down. Easy enough. But then you have the normal force, n, and that one is always perpendicular to the surface of the sphere. So its direction is constantly changing as the body slides. And that changing direction, that's a key part of the puzzle. And here it is. This is the hurdle. The entire problem hinges on what you do with this phrase. This is where most students get stuck, and it's not because the math is hard. It's because they struggle to translate this simple English phrase into a precise physical condition. So let's move on to the key insight, which is how we're going to build our solution. This is the secret that unlocks the entire problem, and once you see it, I guarantee you'll never forget it. First, let's be absolutely crystal clear about the normal force. It is a contact force. Just think about it this way. If your hand isn't touching a wall, it can't be pushing on the wall, right? The force only exists when there is physical contact. No contact, no normal force. Simple as that. Breaking off is that physical moment the body loses contact with the sphere. So, in the language of physics, that just means the normal force disappears. It becomes zero. N equals zero. That's it. That's the whole secret. The entire problem hinges on that one simple idea. Now that we have our aha moments, our physical condition, n equals zero, we just need to apply the right tools from our standard physics toolkit to build the equations. For this problem, we're going to use two of the most powerful principles in all of mechanics. First, Newton's second law, good old F equals ma, to handle the forces and the circular motion, and second, the law of conservation of energy, which is perfect for connecting the body's speed to its position on the sphere. Okay, with our insight, n equals zero, and our two principles in hand, the rest is just careful execution. So let's walk through the math step by step and put it all together. Okay, first, we apply Newton's second law in the radial direction, right at that moment of breakoff. The normal force is zero, so the only force pulling the body towards the center of the circle is just a component of gravity, mg cos theta. That provides the centripetal acceleration, mv squared over r. That's our first equation. Next, we use conservation of energy. The potential energy the body loses as it slides down becomes kinetic energy. This gives us our second equation relating v and theta. And now, look at that. We have two equations and two unknowns. All that's left is to solve them together. And when you work through the algebra, here are your final answers. The body breaks off when the cosine of the angle is 2/3, which is about 48.2 degrees from the vertical. And the velocity at that exact moment is the square root of 2gr over 3. But look, getting the right numbers is satisfying, but it's not the most important part of this whole exercise. The real takeaway here is about the problem-solving process itself. So, the crucial point is this. The most difficult, and frankly the most important skill you've practiced here isn't algebra, it's translation. You learned how to take a real-world physical concept, like an object breaking off a surface, and translate it into a precise, usable mathematical statement, n equals zero. That, right there, is the heart of physics. That's the real lesson from this problem, and it leaves us with a final thought. Where else does this idea apply? Think about a rocket reaching escape velocity or a string breaking under tension. This powerful concept of a force going to zero is a key that unlocks so many other problems. Thanks for joining this explainer.